on machine learning and urban informatics.
All right. Good afternoon, everyone. So my name is Peiyuan. I'm in Discovery Partners Institute as one of the institutes under University of Illinois. So I'm talking about the hyperlocal urban informatics and the three-level temperature estimation, data fusion, and machine learning approach. So when we're talking about the modeling, the skills do matter, right? So on this plot, I just in this plot, I draw all the scales for the data and for the models, right? On the left-hand side, we got the global climate model, which got a 1 kilometer resolution, and on the right-hand side, we got the CFD model, which we talked about just in the previous talk. Here we got trees. The tree seems like to be so small at this scale that when we consider, some regional modeling thing, we cannot accommodate the existence of trees. Why? Because it's so small. But in fact, the urban data in these days already measure a lot of the metrics of trees. See, we have the LiDAR data, which means we have the spatial location for the tree leaves under 1 meter resolution. And also we have the sensor-based observation point, that's point scale. And if we consider to modeling the dynamics over the range, the computational cost is going to increase when we increase the resolution, right? So for the CFD model, we can not really do the real-time prediction, but for the GCM model, we can do the simulation, the future scenario analysis over 100 years. So in the between, we have the urban modeling system and also the new like the coupled LES model and etc. So actually, the urban data sets, we got the meter level rasters that cover classification and also the multispectral satellite image that's still at 1 meter resolution for both of the sites. And we also got a point and vector measurement. So we got a land use inventory that's from the city. They can provide all the building footprint measurement. And we have the environmental observation network sparsely distributed in the urbanized area. The figure here shows the area of the city of Chicago and its surrounding urban area. That's a Lake of Michigan. And in the end, we got the LiDAR point cloud data. It gives you the exact measurement of the location it got returns. So, and if we consider to use all of the data, the best strategy we have now is just average it from the very the detailed LiDAR data to some kind of classification or some kind of land use description. So in this case, we already have the detailed urban morphology. It's just the model, but we cannot take the very detailed data to the simulation. So in this case, we are actually throwing away a lot of information on the data axis. So what do? We want to propose a data-driven modeling framework using the low-resolution model and data and the high-resolution urban informatics. To fuse these two, we need to figure out some machine learning algorithms to do the work for us. So the research question we propose is to find the citywide hourly air temperature at meter level resolution. That's a very bold claim because now we're talking about the meter level resolution at the citywide. So if you go previously, that's almost like the contradicting two things on the axis. But in this case, we will not throw away any information on the data axis. We got the low resolution data and the high resolution data. And I call this the 3 modules in this modeling framework, and they all exist for a reason. For example, the low resolution model and data, they will give you the citywide weather conditions and also the basic intraday variation, physical constraints of the basic weather. For the high resolution urban informatics, it gives you the hyperlocal urban features. And if you have a tree around, if you have a high building around, it's gonna told you what is the intended ground truth about it. And in this urban informatics, we also got the observation sensor, give you the real reading of the environment. And the machine learning algorithms, we need to select the proper algorithm to quantify the relation according to the data types we have for the raster data or the vector and point data. So this is actually the detail of the data-driven modeling framework. In the urban informatics column, we've got observation network, the research-grade weather data, the land cover, the digital land cover from LiDAR, and also the data from satellite imagery that can provide some vegetation phenology, and also the numerical weather forecast models at the state of art itself worth using. And from this side, we start to pre-process the data to do the low-cost sensor calibration and do the spatial aggregation of all the data and to do the time series extraction from the weather forecast model. Then we can have the basic weather condition for the whole cities. Then the model training, model validation, and also the model application. So for the sake of time, I will talk about the low-cost sensor calibration and also the application for the LiDAR data. So the image shows here is actually the LiDAR scan over a street block, and you can see it provides a position of the buildings and the trees, and even the cars in the parking lot, and also gives you the classification of all the points. You got the roofs, the trees, and some low vegetations around there. And this figure actually is a LiDAR over the entire street block and the entire city. It gives you the head information of all the objects, surface objects. You see the trees and the buildings. Then we use the building footprint I mentioned earlier from the vector data to separate the building from the vegetation. And we also compare the data to the LiDAR classification and do the an EBI from the multi-spectrum satellite image and also the meter-level urban classification. In this case, we kind of to build all the data sets that needed to be used in the machine learning algorithm. The other part is the low-cost sensor. Since this one is really important because it provides you the ground truth of what actually the model is learning from it. But the nature of low-cost sensor is just they are not reliable. In this case, we need to cross-compare the results from the low-cost sensors. Say here, as an example, it's an AOT network labeled in red, and compare to it to some research-grade sensors from the West. We form the pairs of it and try to find what is the systematic error from the local sensor to the research. So in this case, we compare all of the pairwise comparison and do the analysis. We can say, okay, there will be some constant bias and also some heating. After correction, we'll have the normalized distributed bias. Say we we somehow correct the data, and this can be used for the ground truth in the modeling system. So this scatter plot shows you the improvement from the basic WRF UCM prediction to the WRF informed machine learning algorithm to the daily scale and to the hourly scale. The improvement is very drastic, and also see the downward variation of the day. The improvement is very drastic. And on this slide, I showed you the model performance regarding to the training ratio, meaning how many data we feed the model, and also the spatial variation of the data. One thing I would like to mention is that the model performs differently from different locations. For example, the station 23 here around the campus of the University of Chicago actually performs really bad if we just train the model without the data from here. Meaning that not all the measurement location is equally important. This indicates that we need to do the observation at some certain locations to further constrain the machine learning model to do its work. And after that, after we collect all the information, we can produce some the temperature heat mapping from the modeling results. So as you can see, if you see a large park over here and over here, you will see a very cool zone around the region and also some high vegetated area. We also need to identify some like the urban features. So you can see that's really the model is really explaining the urban physics that we learned from the other studies. So in the end, I was this is my last slide. So in the end, we can do the what we want to do is the citywide hourly air temperature and meter scale resolution. And and also I want to thank my sponsors for this study, the DOE and the University of Illinois and Water Foundation. Thank you.